Continuing on with our next topic for Chapter 4, which is dilutions. So most of us have some kind of experience in our lives with dilutions, whether you think about it or not. For example, if you've ever bought a concentrated juice from the grocery store, you know it usually comes in those frozen cans, and you take it home and you're not likely to consume that can directly as it is. You're going to put it into a pitcher and you're going to add a bunch of water. Okay, because the juice comes in a concentrated form and you need to dilute it so that it's palatable, right? Well, in chemistry, we have a similar problem where typically what you buy from a chemical distributor is a concentrated version of your solution. So, for example, when you buy hydrochloric acid from a distributor, it usually comes as 12 molar concentrated hydrochloric acid. Right? And 12 molar HCl is guaranteed to burn your face off. So you have to be very, very respectful of it. If you ever find yourself in a laboratory situation playing with concentrated hydrochloric acid, okay? And playing is probably not the right word. But the way it comes from the store is 12 molar. So what happens, what do you do if you need 6 molar? For your particular equation, or for your experiment, that is. So we use the dilution equation to figure out how much water needs to be added to dilute our hydrochloric acid solution. Okay, so the dilution equation takes, you'll see it in many different forms. The equation will always be the same, but typically you'll find differences in notation. They'll use different letters for concentration. The way I learned it and the way that I teach it is M1V1 equals M2V2. M standing for molarity. Okay, and you can think about this as initial final, so initial molarity, initial volume, final molarity, final volume. And you can also find this equation, the other common way that it's given is C1V1 equals C2V2, and C just standing for concentration. Okay, but the way, like I said, the way I'm going to show it and teach it, I use M1V1 equals M2V2. Okay, so let's tackle our question that we have here is how do I get 6 molar hydrochloric acid if I'm starting with 12 molar? Okay, so starting with 12 molar HCl, how much do I need in order to make 500 milliliters of 6 molar solution? Okay, so in other words, what is my starting volume of HCl in order to dilute it to 500 milliliters of 6 molar solution? So if we can think about it, if I'm just going to make this crudely in a beaker, and that's supposed to be a beaker, I need some volume of 12 molar solution to start. And then I'm going to add water to 500 milliliters of 6 molar solution. All right, so I need to know what is that initial volume. So an easy way to tackle these problems is to make a list. So my M1 is 12 molar. My V1, I don't know. My M2 is 6 molar. And my final volume desired is 500 milliliters. Okay, so I'm going to use my dilution equation and just rearrange it. So I'll have 6 molar times 500 milliliters divided by 12 molar. Now, a question that often is asked by students is, do I have to convert my volumes to liters? And the answer is, if you want to. Okay, it's actually kind of optional here because units will cancel out, right? In this case, my molarities are going to cancel out, leaving me with an answer in milliliters, and that's fine. Now, I could convert this to liters. It really doesn't matter. Because if I, say for example, if I'm solving for a molarity and I'll have milliliters over milliliters, the milliliters units are going to cancel out, so it really doesn't matter. Okay, so in this case, I'm going to start with 250 milliliters of 12 molar solution. Start with 250, and then I'll add 250 to get to 500, and that cuts my concentration in half. So let's do another practice problem, because these sometimes are good to do because wording can kind of be confusing. So here's our new question. To what volume should you dilute .2 liters of 15 molar sodium hydroxide, again, guaranteed to eat your face off, but less painfully than HCl will, to obtain a 3 molar sodium hydroxide solution. And I should clarify that previous statement about sodium hydroxide being less painful. So acids tend to activate the pain receptors in human skin. When you get acid on your flesh, you will actually feel a burning sensation. Bases, on the other hand, don't tend to activate your pain receptors, even though they're actually dissolving your flesh. So it's entirely reasonable to get base on your skin and not really even notice that it's being damaged. Your skin will feel slippery, almost like you've got soap on you, and that's quite literally your skin cells dissolving and becoming slick. Nice gruesome way to go about your day. But anyways, let's come back to our dilution problem here. So what volume should we dilute to take 0.2 liters of 15 molar sodium hydroxide, and in order to get a 3 molar solution? Right, so our M1 is the 15 molar, our V1 is the 0.2 liters, 200 milliliters. Our desired molarity is the 3 molar, and our new volume, we don't know. All right, so what will be our new volume? So V2 is M1 V1 over M2. Molar times 0.2 liters divided by 3 molar. These are supposed to be M's. I'm sorry for my handwriting. And we'll find that we need to dilute this to 1 liter. All right, so the way this will work in the laboratory is you'll take a 1 liter volumetric flask. And the volumetric flasks are the ones that have the long neck and the sort of bulbous bottom. And they've got a line here. And that line, and it'll say 1 liter on it. So that line tells you 1.00 liters. Okay, so I'm going to start by putting in 200 milliliters of 15 molar NaOH. So that'll take up about this much, right down at the bottom. and then I'll fill to 1 liter. Okay, and the result will be I'll have my volumetric flask, my 1 liter volumetric flask, now with 3 molar NaOH. Okay, so dilutions are super important, and you're going to, if you continue on very far into chemistry, get into quantitative analysis lab or organic lab, dilutions will happen all of the time. So let's move on to our next topic, and we're going to start talking about acids and bases. All right, and the simple version of things is that acids are proton donors. And bases are proton acceptors. Okay, so we're going to have a transferring of a hydrogen ion, an H+. Right, so when we're talking about protons, we're talking about H+. Okay, because a hydrogen atom with no electrons on it is nothing but a proton. Okay, so acids differ in the number of protons they can donate. That word says number, N-U-M-M, N-U-M-B-E-R, in the number of protons. In the number of protons they can donate, and with the ease with which they can donate them. Okay, so some acids donate protons better than others. Some acids have more protons to donate than others. And I think I'm actually going to stop this video right here because we only have about a minute left on our 15-minute time frame. And it's about time to start our morning Zoom meeting. So we'll pick up right here with acids and bases when we get back.